Hello and welcome to lecture number 11 for the course ECE 257A, Fault-Tolerant Computing. This lecture is the first of two on part 5 of the textbook dealing with malfunctions. Now, malfunctions is a word I use for what in the literature is sometimes referred to as system-level faults. We talked about faults before, logic faults, where logic faults are basically things that can happen at the gate and interconnection levels, like a gate does not work correctly or a wire is disconnected. So those are logic faults. At the system level, we deal with larger units that can be malfunctioning, so to speak. So a processor unit can be malfunctioning, memory unit, disk unit, and so on. So we are talking at a higher, much higher level. And in order to distinguish these kinds of faults from the faults that can occur at the gate level, at the logic level, sometimes we use the term system level faults. Okay. Now, because of the terminology we use, we don't have to use the qualifier system level because malfunction is the word we use for a system level fault. So that's one of the advantages of the terminology that I've used in this textbook. We don't have to use all these qualifiers because we have a specific word for system level faults. Okay, so part 5 of the textbook consists of chapters 17 through 20. And according to the usual pattern, I'll cover chapter 17 and 19 in this lecture, and chapters 18 and 20 in lecture number 12. Okay, so the first part of today's lecture is malfunction diagnosis. Basically determining that something is wrong at the system level in the modules that are interconnected to form the system. Okay, one of the ways in which we can diagnose malfunctions is through self-diagnosis. Because we are talking about units that have rather significant functionality. If you talk about processor, memories, nowadays, memories have memory controllers that are pretty intelligent. They're almost like a full-blown processor. A disk drive has a controller that is, again, like a processor. So these units, because of the built-in intelligence, can do a lot in order to diagnose their own internal problems, internal faults. Okay, so self-diagnosis is one of the ways in which these units can basically determine that something is wrong. Okay, of course, the natural question is that how can you trust a unit that is malfunctioning to diagnose itself? Because if something is wrong with it, how can you trust the outcome of its self-diagnosis? One of the ways in which we achieve this type of self-diagnosis is through a layered approach. And this is basically what happens when you boot up a computer. It goes through a self-diagnosis routine to ensure that the system is okay and can basically start operating safely. So what is a layered approach? First, a small part of the unit is tested. So a kernel, a small part of the unit is tested. Okay, we basically use a fairly extensive set of tests to determine that this kernel is working correctly. And then we use the kernel to diagnose unit A maybe, and then now we trust this part of the system. Then we use those trusted parts to diagnose unit B. So we basically extend the trusted part of the system until it covers the entire system. So an example of this, the kernel may be the main part of the processor, let's say the instruction execution unit, and some basic parts of the ALU. Once that part is tested, we can probably use the rest of the ALU, any coprocessor that we have, any memory units, any disk drives, and so on. So that kernel, because it's fairly small in size, you can afford to test it exhaustively. Or I shouldn't say exhaustively, extensively. And then be fairly confident that it works correctly before proceeding to self-test the rest of the system. So this is basically the way self-diagnosis works in most modern systems. Okay, now the systems you use nowadays are basically collections of modules that are connected to each other. As I mentioned, the modules can be a processor, one or more memory units, one or more disk drives, network controllers, and so on. Or they can be computer networks of full-blown computers. So one approach to do go, no-go testing. Go, no-go testing is basically a test that says whether a unit is okay or not okay. We don't try to diagnose, what's wrong internally to that unit. We just want to determine whether that unit is okay or not okay. So that's called a go, no-go test. We can do this based on self-diagnosis in the following way. So for example, let's say unit A is such a unit that has internal intelligence and can do self-diagnosis. But as I mentioned, we can't trust unit A to test itself if it's not actually working correctly. So one way to do it is to supply what we call a seed to that self-diagnosis unit. So the self-diagnosis unit basically runs a program. And that program puts the various parts of that unit through its paces. It basically asks various parts to do things. And then depending on the initial seed that you provided, it can generate an outcome or result. And that result will be dependent on the initial seed. Okay? So let's say the kernel supplies that seed to unit A. Unit A runs its self-diagnostic with that seed and comes up with an answer, and it sends the answer to the kernel. And the kernel knows what the outcome of that self-diagnosis should be with that particular seed. If the outcome matches the expected outcome, then the kernel concludes that unit A and its self-diagnosis routine are okay, and therefore it can trust unit A, extend the domain of trust, and then go to unit B and then to unit C. Okay, so rather than the kernel trying to supply a whole bunch of tests to unit A, which can take a long time and require a lot of communications between the two units, it can supply just one seed, maybe 32 bits or 64 bits or 256 bits, whatever the seed size is. A limited amount of information. Then unit A uses that seed as part of its diagnostic unit. So for example, it's an operand that the diagnostic unit operates on, and it sends that to the ALU, it sends it to memory, tries to test various parts. of the unit, and then at the end it comes up with a result based on that seed. And then it sends that result back to the kernel, and the kernel knows it may have a table that says for that particular seed, the expected result from unit A is this. So if the expected result matches the actual result, then unit A can be trusted. Okay, if this return value, let's say, is 32-bit, the chances are slim that the correct 32-bit value is supplied by a malfunctioning unit. If you properly design the self-diagnostic, okay, it's very unlikely that the exact correct 32-bit result will be generated by a malfunctioning unit. It's very likely that something different will be generated, and therefore the malfunction will be detected. Okay, so this is basically the idea of self-diagnostics and mutual diagnosis. So mutual diagnosis between kernel and unit A may involve the kernel sending a seed to unit A, receiving a result, and then judging the health of unit A based on the received outcome. Okay, based on this foundation, if we have a bunch of units connected to each other. Now, these units can be different units within a computer, as I mentioned, CPU, memory, disk, network controller, and so on, or they can be different nodes in a computer network. Doesn't matter. The methods are the same. So suppose we have what we call a testing graph. These are basically a bunch of directed links connecting these nodes to each other. And the meaning of a directed link is that unit M0 tests unit M1. Unit M1 tests unit M2, unit M2 tests unit M0, and so on. So these directed links basically tell us which unit will test which other units. So it's called a testing graph. Of course, in order for the testing graph to make sense, there should be a connection from M0 to M1. So if this is a bus-based system, then of course everything is connected to everything else. If this is an actual network, then we need to have these connections between the nodes. There may be other connections that are not shown here. So for example, M0 may also be connected to M3, but that's not part of the testing graph. So we don't use M0 to diagnose M3. We have not included that link. Okay, so a tester unit I can test a unit J, and there are two possible outcomes, 0 or 1. The outcome 0, so remember, as I mentioned, unit I can send a seed to unit J. Unit J does a self-diagnosis, and then it returns the result to unit I. So this directed arrow does not show the return. It simply says that I test J. But I testing J involves sending a seed and receiving a result. Okay? So the outcome 0 means that unit I thinks that unit J is okay. In other words, based on the seed that was sent and the result that was received, I renders the judgment that it thinks unit J is okay. Of course, this judgment may be incorrect, but that's really the challenge of the diagnosis problem. Or unit I may think that unit J is not okay. Again, it may be erroneous in this judgment, but we have to work with these imperfect results. So unit I testing J has an outcome 0, meaning I thinks J is okay, or outcome 1, meaning I thinks that J is not okay. And the verdict of unit I about unit J is denoted by Dij in 0, 1. 0 means I thinks J is okay. 1 means I thinks J is not okay. All the diagnostic verdicts constitute an n by n diagnosis matrix D, whose elements are these Dij. The diagnostic matrix D is usually sparse because we will have D01 because unit 0 tests unit 1, but we don't have D10 because unit 1 does not test unit 0. So many of the entries of Dij may be 0 because no testing takes place for that particular combination. Okay, so this is an example of a diagnosis matrix. D01 means judgment of unit 0 about unit 1. D12 means judgment of unit 1 about unit 2. Now this matrix is often sparse, as I mentioned. It's also anti-symmetric, usually. If unit 0 tests unit 1, then we don't allow unit 1 to test unit 0. Usually, this is the usual way we use this type of diagnosis. Because if there is mutual diagnosis, 0 testing 1 and 1 testing 0, it's much trickier to deduce the health of the units, as we will see in a minute. Okay? So it's anti-symmetric, meaning that if this entry D01 exists, then D10 does not exist. If D20 exists, then D02 does not exist. Also, diagonal entries do not exist because a unit does not test itself. Okay, units test other units according to the testing graph. Units do not test themselves, and also we usually preclude the possibility that two units test each other. Okay, one unit can test the other one, but not the other way around. Now this model that I just described is known as the PMC model. Is the most commonly used model of diagnosis, malfunction diagnosis. And PMC stands for the initial of Preparata, Metze, and Chien. The three researchers who basically first dealt with this model. There are also other models, including what is called the comparison model. So here, the PMC model relies on the judgment of one unit regarding another one. The comparison diagnosis model is based on two units basically performing the same computation, and the judgment about their health based on comparing the outcomes. So if the outcomes match, then we conclude that both units are okay. If the outcomes do not match, then we conclude that one or the other one, we don't know which one, is not okay. So basically, if we do a whole bunch of these pairwise computations, and then we know, for example, let's say we have units 1, 2, 3, and 4. Let's say 1 and 2 do the same computation, and they disagree. So the conclusion is either 1 or 2 is malfunction. Let's say 2 and 3 also perform the same computation, and they disagree. Then we conclude that units 2 and 3, one of the units 2 or 3 is malfunctioning. And then based on this global information about disagreements between pairs, we try to deduce which units are actually malfunctioning. So that's called the comparison model. We won't talk about that. We actually don't even cover the PMC model in, in great detail. There's a lot more to say than what we can afford to cover given the limited time that we have. So the only model we cover is the PMC model. Okay, so let's say we have this 4-module system and we have done a bunch of tests, and these are the outcomes. So D01 is the outcome of M0 testing M1 and so on. And these are the outcomes. Of course, if all the modules are okay, then all of these test results should be 0. Remember, 0 means that the unit thinks. So if all 4 units are working correctly, then M0 testing M1 will conclude that it works correctly, and so on. So the syndrome of this testing scheme will be all zeros, and that corresponds to no malfunctioning module. Okay, I forgot to mention one thing. When a healthy module tests another module, we assume that the outcome is trustworthy. In other words, if we know that M0 is a good module, is a healthy module, and M0 says that M1 is not good, is malfunctioning, then M1 is actually malfunctioning. Or if M0 says M1 is good, and M0 is known to be good, then M1 is really good. However, if M0 is malfunctioning, then we can't trust the outcome of a testing M1. Okay, so if we somehow know that M0 is malfunctioning, then we can't rely on this test result. Okay, so that kind of test we denote like this. The outcome can be 0 or 1. We don't know which one. It's basically random. Okay. Now, if M0 is malfunctioning, this will be the syndrome. In other words, if M0 is malfunctioning, M0 is the only unit that is malfunctioning, everything is okay, then M2, which is good, will detect that malfunction. Okay, so DT20 will be 1. M3, which is good, will detect that malfunction, so D30 will be 1. However, D01, because M0 is malfunctioning, D01 can be 0 or 1. Okay, so notice that this case that we have, the two cases that we have no malfunctioning unit versus having only M0 malfunctioning are distinguishable because we have a 1 here and a 0 here. So the two signatures are distinct. Okay, the two signatures may not be distinct in this entry because we can have 0 here, and that 0 cannot be distinguished from that 0. However, if there's at least one of these tests whose outcome is different for the two fault patterns, malfunction patterns, then we can distinguish those two. So if M1 is malfunctioning, it's easy to verify that this is the signature. So there are really 4 possible signatures depending on whether this is 0 or 1, or this is 0 or 1. Again, this signature is distinct from M0 malfunctioning because these two are different. And it's distinct from no malfunction because these two are different. This is 1, this is 0. And these two are also different, M0 malfunctioning versus M1 malfunctioning, because they're different here. Okay, similarly for M2 and M3. But as long as you have a single malfunction or no malfunction, these test outcomes, the syndrome, basically tells you whether you have no malfunction or you have one of these cases, because all the signatures are distinguishable. So M3 from M0 is distinguishable. M3 malfunctioning versus M0 malfunctioning. The two cases are distinguished. However, if you have two malfunctions, let's say M0 and M1, this will be the signature. Okay, and this signature is not necessarily distinct from only M0 being malfunction, because they can match in this first entry. This can be 0 or 1, this can be 0 or 1. So the two highlighted rows can be identical. This is 0, but this can also be 0. This is 0, this can also be 0. 1 matches 1, 1 matches 1, 0 matches 0. So the two cases of M0 being the only malfunctioning module, or M0 and M1 being two malfunctioning modules, are not distinguished. Okay? So we say that this system is one step, one diagnosable. One step means you just run these diagnostics once, and based on the outcomes of those diagnostics, you can tell immediately in one step what is wrong with it, as long as the number of malfunctions does not exceed 1. Okay, so we can use a dictionary basically. The syndrome, all zeros correspond to OK. This has two syndromes, 0, 0, 0, 1, 1, 0, and 1, 0, 0, 1, 1, 0. So 0, 0, 0, 1, 1, 0, that means M0 is malfunctioning. And 1, 0, 0, 1, 1, 0 means M0 is malfunction. Okay, so basically if we run the diagnostics and find the syndrome, the 6-bit basically syndrome, we can consult this dictionary, syndrome dictionary, and read out directly which unit is malfunctioning, as long as we are sure there's just one, at most one malfunctioning unit. So this is known as one-step diagnosability. This system is one step, one diagnosable, meaning that one malfunction can be diagnosable. We'll see later that this system cannot be two diagnosable. Okay. We prove it. Actually, here we observed that it's not two diagnosable, because if you have two malfunctions, the signature may be indistinguishable from a single malfunction. Okay. Oops. Okay, so here we talk about requirements for one-step T diagnosability. An N-unit system is one-step T diagnosable. In other words, we run one set of tests shown on the diagram, and up to T malfunctioning unit can be directly identified. This happens obviously if the diagnosis syndromes for conditions involving up to T malfunctions are all distinct. Okay, we have two necessary conditions for this to hold, one-step T diagnosability to hold. First, the number of modules N must be at least 2 times T plus 1. For T diagnosability, we must have at least 2T plus 1. In other words, a majority of units must be good. This is an absolute requirement. So that's why this system with 4 modules can never be two diagnosable, no matter what the testing graph is. Okay, you may have thought that, okay, this was not two diagnosable. Maybe if we add more tests, it becomes two diagnosable. A 4-module system can never become two diagnosable, because a majority of the units must be good. And if 2 units are bad, there are two good units which are not in the majority. And each unit must be tested by at least t other units. So there are two necessary conditions, n greater than or equal to 2t plus 1, and each unit must be tested by at least t other units. That also tells us that this system cannot be two-diagnosable because M1 is being tested by only one unit. Okay? If we want this to be it can't be with 4 nodes, but even if it had 5 nodes and we had this situation that M1 was diagnosed only by one unit, then it could not be two-diagnosable. So that's necessary condition. A sufficient condition is this: an n-unit system in which no two units test one another is one-step t-diagnosable if and only if each unit is tested by at least t other units. Okay, so if we have this requirement, that this condition that no two units test each other, that's obviously satisfied in this graph. M1 tests M2, M2 does not test M1. So there are no links, directed links in both directions. Okay, so that requirement is satisfied. So an n-unit system in which no two units test one another is one-step t-diagnosable if and only if each unit is tested by at least t other units. So here M1 is tested by one unit, M2 is tested by two units, M3 is tested by one unit, and M0 is tested by two units. So the minimum number of units that test a particular unit is 1. Therefore, this has the necessary and sufficient condition for being one diagnosable. So I really didn't need to form this table because this result tells me, of course, I haven't proven this result, but the proof exists. So this unit, by just looking at this testing graph, we could tell that it is one step, one diagnosable, and we could also tell that it cannot be two diagnosable. Okay, there's an analogy, basically the challenge of determining which units are malfunctioning exists because sometimes a malfunctioning unit gives us information about another unit, and we somehow have to weed out that incorrect information. Okay, there are some puzzles about, an island in which there are two tribes. One tribe consists of liars, and another tribe consists of truth tellers. And the challenge of determining, by talking to these people, which ones are truth tellers and which ones are liars. Okay, so I won't say more about this. So that's why the problem is challenging. So one-step diagnosability, with regard to one-step diagnosability, we have two set of problems: analysis problems and synthesis problem. Analysis problems are two of them. Given a directed graph defining the test links, find the largest value of t for which the system is one-step t-diagnosable. In other words, I give you the testing graph and then ask you, is this system, let's say, 3 diagnosable or 4 diagnosable? Or what is the largest value of t for which the system is t-diagnosable? And you have to come up with the answer. Another analysis problem: given a directed graph and its associated test outcomes, identify all the malfunctioning units, assuming that there are no more than t. Of course, if the system is t-diagnosable, we won't allow more than t malfunctioning units because that diagnosability is only guaranteed up to t. But which t of the units are malfunctioning? Okay, so for example, in this in this Yeah. In this diagnosis matrix, these entries are given to you. These are zeros and ones. And your job is from this matrix determine which unit is malfunctioning. Okay, that's the second analysis problem. The synthesis problem is basically a design problem. Okay, you want to design the testing graph so that the system is one step T diagnosable using as few test links as possible. You want to minimize the number of tests, but still guarantee that the system is one step T diagnosable. Okay, this problem actually we already know an answer, but there, you may look for better answers, different answers that are more in line with the system's architecture. So if you have an n-node corridor ring in which node I is connected to node I plus 1, I plus 2, I plus 3, I plus T, then this system is guaranteed to be one step T diagnosable. So in this example, I have not shown all the testing links. There are the green links going from node I to node I plus 1, blue links going from node I to I plus 2. So similarly, there will be a blue link between these two, a blue link between these two, and so on. And then the red links going from node I to I plus 3. So there's one of them. Here is another one. Here is another one, and so on. So if I provide all those testing links in this corridor ring, then the system will be 3 diagnosable. Okay? It already satisfies the necessary condition. If a system has to be 3 diagnosable, it must have at least 7 nodes. Okay? So it satisfies that necessary condition. Node I is connected to node I plus 1, I plus 2, I plus 3. There are 7 nodes. T is equal to 3, and the system is 3 diagnosable. Okay, but if your system has a different architecture, you have a network that doesn't have these connections, then you may want to design another testing graph to ensure 3 diagnosability. But there's at least one answer to that question, okay, of specifying the test links or the connection assignment makes an n-unit system one step T diagnosable. Okay, with respect to the diagnosis algorithms given the test outcomes, a naive algorithm is order n cube in running time. You basically have to label all the nodes with good or bad, that's the outcome. So the diagnosis matrix is your input, your output consists of every node, every unit labeled good or bad. So here's the algorithm. While some units remain unlabeled, repeat this process. Choose an unlabeled unit and label it G or B. Use labeled units to label other units. I'll talk about this in a second. If the new label leads to a contradiction, then backtrack and change the labels that you assigned previously until you get to the end of the process and no contradictions arise. So here is an example. Suppose I assume that M0 is good. So I label M0 with G. Okay, that's an arbitrary choice. I could have started with B, bad. Okay, so I start with M0G. Then if M0 is good, M1 must be bad given this test outcome. Because a good module always makes the correct diagnosis about another module, and this test outcome is 1. Therefore, if M0 is good, M1 must be bad. Okay? M2 must be bad too, because M2 is saying that M0 is bad, but M0 is good. We assume that it's good, so M2 must be bad. here's a contradiction because I identified two bad modules, whereas I assume that there's no more than one bad module. So I backtrack and say, okay, M0, which I assume is good, that assumption was incorrect. Let's say M0 is bad, okay? And so on and so forth. So this is an order n cube algorithm. More efficient algorithms exist. For example, this is an order n to the 2.5 step diagnosis algorithm. From the original testing graph, we construct something we call the L graph. The L graph has the same nodes, the same 4 nodes as the original testing graph. Okay, there's a link from node I to node J in the L graph if and only if node I can be assumed to be malfunctioning when node J is known to be good. Okay, so for example, if node M0 is known to be good, then M1 is malfunctioning. Okay, so when we can assume that the node is malfunctioning when another node is known to be good, M0 is known to be good, leads to the conclusion that M1 is malfunctioning. So there is a link from M1 to M0 in this graph. Okay, similarly, if we know that M1 is good, if M1 is good, then M0 must be malfunctioning because of this test outcome. Because a good module does not make an incorrect diagnosis. So if M1 is good, then M0 must be bad. So that's the reason for this link. Okay, so in this way, I can construct this L graph. Now, vertex cover of an L graph is the set of malfunctioning nodes. And vertex cover is basically a set of vertices that touch all the links. And M0 is such a vertex cover because M0 touches all the links in this L graph. Therefore, M0 must be the malfunctioning unit. Okay, so from these test outcomes, when I find the vertex cover, the minimal vertex cover of this graph, which is M0, that tells me the malfunctioning units. Okay, so I basically converted the problem of finding the malfunctioning unit in this problem to finding the vertex cover of another graph that can easily be constructed. Okay, the next idea is that of sequential diagnosability. So one-step diagnosability means in one step, we just say, okay, let's say we have a whole bunch of modules, 10 modules. We say, okay, M0, M3, M5 are the malfunctioning units in one step. Okay. In sequential diagnosability, the requirement is for us to be able to identify one malfunctioning unit. Okay. So for example, this is a 5-node unit. And we know that it's not one step 2 diagnosable because each unit is tested by just one unit. So it can't be 2 diagnosable, one step 2 diagnosable. But it is sequentially 2 diagnosable. What does that mean? Means that if you have up to 2 malfunctioning units, you are able to identify one of them. And then you basically remove that. Let's say M1 and M3 are malfunctioning. You are able to identify M1. You remove M1, replace it with a good module, and then now you have only one malfunctioning unit. And in the second phase, so it's not one step, it's multiple steps or phases. In one step, you identify one malfunctioning unit, and in the next step, another malfunctioning unit, and so on. So an n-unit system is sequentially t-diagnosable if the diagnosis syndromes, when there are t or fewer malfunctions, are such that they always identify unambiguously at least one malfunctioning unit. As I mentioned, this is useful because some systems that are not one-step t-diagnosable are sequentially t-diagnosable, and this is a simple example. This is not one-step two-diagnosable, but it is sequentially two-diagnosable. So for sequential t-diagnosability, we still need to have a majority of the units good. That's a necessary condition. And for directed rings, an n-node directed ring is sequentially t-diagnosable for any t that satisfies this equation. The next slide is a little bit more detailed. So this is a 7-node directed ring. And because t equals 3 satisfies this inequality, 3 squared minus 1 divided by 4, so that's 9 minus 1 divided by 4 is 2. 2 plus 3 is 5. 5 plus 2 is 7. It is less than or equal to 7. Therefore, this is, sequentially re-diagnosable. Okay, we already know it can't be 4-diagnosable because majority of the units could be good. So 3-diagnosability is the best we can hope for, and this actually has that property. Okay, so this is basically sequential 2-diagnosability of a 5-node ring. I formed the syndrome table. No malfunction is all zeros. I've excluded that row. M0 malfunctioning, this is the syndrome. X means 0 or 1. M1 malfunctioning, M2, M3, M4. M0 or M1 malfunctioning. Okay, this syndrome is indistinguishable from M0. So that's why it's not one-step two-diagnosable. Because this first X can match that X. They can both be 0 or 1. This X can match that 0. This can be 0, 0, 0, 0, 0, 1, 1. However, in both of these malfunction patterns, M0 is malfunctioning. Therefore, even though these two are indistinguishable, they both tell me that M0 is malfunctioning. So I can go ahead to remove M0, replace it with a good module, and run the diagnostics again to find the second malfunctioning unit if there is one. Okay, again, for sequential diagnosability, we have analysis problems and synthesis problem. Given the directed graph defining the test links, find the largest value of t for which the system is sequentially t-diagnosable. That's one analysis problem. Given the directed graph and its associated test outcomes, identify at least one malfunctioning unit, preferably more. If you can do more, then obviously it's better because you need fewer steps. At least one malfunctioning unit, assuming there are no more than t malfunctioning units. And the synthesis problem, as before, is specify the test links or connection assignment that makes an n-unit system one-step t-diagnosable. Again, the next slide is more elaboration. Oops. No, there's no others. Sorry. So an n-node ring with n greater than 2t plus 1 with added test links from 2t minus 2 other nodes to node 0, okay, has the required property. Okay, I meant to include an actual diagram of this ring, but I forgot to do it. Sorry. So we know at least one architecture that is sequentially T diagnosable. We may want to have uh, other test graphs that are more in line with the connections between modules that we already have in our system. Okay, I'm going to skip this section about diagnostic accuracy. Basically, so far we limited the diagnostic schemes to identifying bad modules. In other words, in one-step diagnosability, we identify all the bad modules at once. In sequential diagnosability, we identify one bad module, but there's no doubt that that module is bad, and we remove it. So if we are willing to allow less accuracy, in other words, we say we want to have two diagnosability, but we are willing to sort of identify three modules that have both of the bad modules. If that's acceptable, then it's easier. We can sometimes guarantee two diagnosability if we allow three modules to be removed. So in this case, one of the modules that is removed is a good module. So it's sort of viewed as wasteful that we remove three modules in order to guarantee two diagnosability. Then on the other hand, the modules that are removed can be tested, and if a module is good, it can be returned to service later and not discarded. So it's really not wasteful in that sense. It allows us to diagnose the system more conveniently. Okay, so this is the idea. If we are willing to allow less accuracy in diagnosis, then we can do more with diagnostics. Okay, there's a whole uh, a bunch of papers in the literature that deal with diagnosability of well-known architectures, regular or irregular architectures. And you can look these up if you, for example, if you're using a corridor ring, then you can look up in the literature to see what people have discovered about the diagnosability of corridor rings or hypercube or torus networks and so on. So what comes after malfunction diagnosis? So suppose you diagnosed the bad modules, the malfunctioning modules. What next? Well, I mentioned that you need to remove them, but how do you actually remove the modules? So usually removal is done through reconfiguration, and that's the topic of the next chapter that I'll cover. You have to recover state information from removed modules. So for example, if those modules have memories, you have to sort of preserve the memory contents, either from a backup copy or from the modules themselves, if the memory has not been affected by the malfunction. You have to reassign tasks and reallocate data to other modules that will take the place of the malfunctioning module. Sometimes you have to restart the computation from the last checkpoint or from scratch. We'll cover checkpointing in a later chapter. In a bus-based system, we have to isolate the malfunctioning unit from the bus so that it doesn't cause trouble for the other remaining good modules. Because if the unit is malfunctioning, it can do unpredictable things and therefore cause trouble on the bus that the good modules are using. Okay, in a system having point-to-point connectivity, we reconfigure by rearranging the connections in order to switch in spares, and this we'll talk about later. All right, so chapter 18 will be in the next lecture, so let me proceed to chapter 19, standby redundancy. Okay, in order to use standby redundancy, meaning that you have an operating module and you have spares that can take its place, you need to detect malfunctions. Okay, we just talked extensively about malfunction detection in a system. So malfunction detection can be done through various methods. Periodic testing is one of them. So if you have a testing graph, periodically you basically shut down the system and run your diagnostics and then determine which modules are bad and then do something about them, remove them. You can have self-checking design. Modules are self-testing, self-checking and self-testing so that they can identify their own problems as they're running computations. You can design modules to be malfunction stop or malfunction silent, meaning whenever something goes wrong with them, they basically shut down. So they don't mislead. They never mislead other units by sending corrupted data, bad data. They just shut down. And that's basically a better situation than if they continue running and supply incorrect data to other parts of the system. So malfunction stop operation is eventually detectable by a watchdog. So if you send, for example, a request to such a module that has shut down and it doesn't respond after a certain reasonable time period, then you assume that it is malfunction. So remember, in all of these schemes that we have talked so far, we have discussed so far, malfunction detection comes with some delay. So if you do periodic testing, depending on the period, you don't detect the malfunction right away. Okay, you have to wait until the next testing phase until detecting the malfunction. If you have a malfunction stop arrangement, then you may not detect the malfunction right away, but you will eventually detect. Okay, and we can do coding, code the data. This is particularly suitable for memory and disk storage modules. Data is coded, so whenever the coding scheme is violated, you know that something is wrong. So that's basically immediate detection of the malfunction. And you can do monitoring, and these are ad hoc schemes based on application and system dependent considerations. So you basically, for example, if a processor is connected to a bus, you can have a unit, a monitor looking at the bus, and then basically determining that the processor is doing reasonable things on the bus. It's sending addresses, it's receiving data, and so on. And if it detects some sort of abnormal communication or behavior on the bus, it assumes that something is wrong. Of course, monitoring is not 100% foolproof, but it can detect, a large fraction of typical malfunctions. We can code control signals. For example, here you see a microprogram control unit where micro instructions are read from the microprogram memory, and the micro instruction is used to control. It contains control signals for the data path. It also contains a field, in this case, in this example, 2 bits, that indicates which micro instruction should be fetched next. So one micro instruction is fetched. It controls the system for one cycle, one clock cycle, and then it also determines the next micro instruction. And the next micro instruction has 4 options. It can be micro instruction 0. You basically go to the beginning of the microprogram. It can be the next micro instruction in sequence. You basically microprogram counter incremented by 1. So basically that's when you have multiple micro instructions in sequence defining a particular instruction. Or it can come from tables that's basically jump within your microprogram. And that those jumps can be instruction dependent. So if you're executing an add instruction, for example, and you have done operand fetch, then you go to a particular micro instruction to do the actual addition. If you're doing multiply, then you go to a different micro instruction. So the opcode determines which entry of the dispatch table dictates the next micro instruction. Okay, so these are things that you should know from computer architecture. The parts that are new here is that the micro instruction can be encoded by using check bits to make sure that the microprogram memory contents is not corrupted. Also, it may contain an address field in it so that when you fetch a micro instruction from a particular address, you can ascertain that it actually came from that address. In other words, the decoder of this memory also worked correctly. So you compare this address to the address from which you fetched to make sure that you actually read correct micro instruction. So you read the correct micro instruction, and that micro instruction has not been corrupted because you have check bits, you have error codes there. Okay, the next couple of slides basically lists a whole bunch of things that you can do in terms of monitoring using, say, watchdog timers. So for example, if a function unit does something and there should be a reaction to that thing within a certain time period, a watchdog timer can detect that that time limit has been exceeded and therefore something is wrong. Okay, I won't go through the details of these 2 slides. Also, activity monitor can do similar things to check whether the activity of the function unit are reasonable or what we expect. So for example, one of the things that can be done in practice is monitoring a program sequencing. So when you write a program, that program consists of instructions that are executed in sequence, and there are occasional branches or jumps. Okay, so if your program has a jump to a certain location, the jump is executed that goes to a different location, a location that is unexpected, that can be detected. So that is known as program sequence monitoring. So you monitor that the program is actually going through steps that you expect. And those steps can be sequential execution of programs or jumps to specific locations. If there's a jump to an unexpected location, then something is wrong. Okay. So when we use spare units, those spare units are characterized as being hot spare units. Basically a spare unit that is running in parallel with the main function unit. And therefore, if the function unit malfunctions, this spare unit is completely ready to take over because it was basically doing the same things as the main unit, and therefore is exactly in the same state as the main unit. That's a hot spare. A cold spare basically is powered off, and therefore if you need to bring it in, it has to be powered on. It has to be initialized, its memory and other parts, program counter and everything, initialized to the correct values before it can step in and take over from the malfunctioning unit. So this takes some time, and therefore it's less desirable. But of course, it's more desirable in the sense that using less energy because it's powered off. And also, usually a unit that is powered off has a lower failure rate. So it's less likely to fail in the powered off mode than if you use it as a hot spare. Intermediate between cold and hot spares, we have warm spares. For example, a warm spare may be powered on, but it's not actually doing the same computations as the operational unit. So you basically save energy because it doesn't undergo signal transitions and other things that consume energy. Okay, there's nothing in this section yet. Now, when we talk about spares, the first thing that comes to our mind is some scheme like this, where you have an active unit and there's one or two or more spares here. For this, you need an N-to-1 switch so that whenever this malfunctions, this unit malfunctions, and it's detected here by whatever means, then one of the spare units steps in by configuring the switch to use this output instead of this output. Now this is a high redundancy scheme, and it's less desirable than low redundancy scheme. So here's an example of a low redundancy scheme. So here I have a 4x4 array of processors, and some of them can malfunction, but I don't want to provide 16 spare units so that each one of these has a dedicated spare unit. I may choose to provide only 4 spare units, these green circles, so that this spare unit can replace any one of these 4. So as long as only one of these units malfunctions, this spare unit can take over, and so on. So it's much less redundancy. There are only 4 spares for 16 units. Okay, so it's only 25% redundancy rather than 100% for one spare. However, there's a challenge here. Now, if I have a 4x4 processor array, so that this processor is communicating with these 3 processors, it has 3 neighbors, so to speak, then if this one wants to take over for this one, it better be able to communicate with this, and with this. If it wants to take over for this one, it better be able to communicate with this and this. If it wants to take over for this one, additionally, it has to be able to communicate with this one and this one. And finally, if it wants to take over for this, it should be able to communicate with this one and this one. Okay? So this spare unit has to have a lot more communication link compared to the regular units in this. So the maximum number of links in this 4x4 array is 4, whereas this spare unit must be able to connect to 1, 2, 3, 4, 5, 6, 7, 8 units. Okay, so this is a challenge because now the spare unit will not have the same design as the original unit. And furthermore, it has to have 8 communication ports, which adds to its cost and energy consumption, and it has to be specially designed rather than just being a replica of this or this. Okay, so it's non-trivial to do this kind of low redundancy sparing. Okay, this section again has nothing in it, and this section doesn't either. So that's basically all I want to say in this lecture. Next time we cover the remaining two chapters of part 5. All right, bye for now. Stay safe until the next lecture.